Hello everybody, welcome back to our network flows unit. Today we're going to talk about an application of some of these network flow algorithms we've been discussing to a problem called bipartite matching. So, to get started on this, suppose that you're trying to coordinate housing in a college dormitory. So, what you have is you've got N students and M rooms. Each student is giving you a list of rooms that they consider to be acceptable. And what you'd like to do is place as many students as possible in an acceptable room. Now, of course, there's a limitation here that you can't place more than one student in the same room. Okay, so this is the problem. How do we organize this data? Well, you've got a bunch of students, and you've got a bunch of rooms, and there are some pairs of students and rooms where that student is willing to be in that room. And so a great way to organize this data pictorially is by what's known as a bipartite graph. A bipartite graph is just a graph G where the vertex set can be partitioned into two subsets, U and V, students and rooms. There's sort of two types of vertices, such that all edges in the graph are between a vertex of U and a vertex of V. So all the edges connect a student to a room, not a student to a student or a room to a room. And so if we just redraw that graph and call the two sides U and V instead of students and rooms, it's exactly a bipartite graph. So what we'd like to do on this graph is find what's called a matching. We want to find a bunch of pairs of students and rooms. That's a bunch of edges of the graph. But it needs to be the case that each student gets assigned only one room and each room is assigned to only one student. And that says that no two of these edges that we pick can share an endpoint. So in our example, if you look at the blue edges here, that will give us a matching. We've got a bunch of pairings of students get paired to rooms that they were acceptable to be paired with, and each student is assigned only one room. Each room is assigned to at most one student. Fine. So the big problem we're going to be trying to solve is known as bipartite matching. Given a bipartite graph G, we'd like to find a matching of G that consists of as many edges as possible, and ideally one that pairs up all of the vertices with each other. So just to be sure that we're on the same page, if I give you the following bipartite graph, what's the size, the number of edges in the largest possible matching? Well, you have to play around with it for a bit. You can find that you can actually get matchings of size 3 here, and it takes a while, but you should be able to convince yourself that it's not actually possible to get a matching here of size 4. Fine. So let's talk about applications. Bipartite matching actually has a bunch of applications. One thing maybe is matchmaking. Suppose you have a bunch of men and women, some pairs of them are attracted to each other, and you would like to sort of pair them off into as many possible couples as possible, such that, nobody's dating more than one person at the same time. Now, we have to be a little bit careful here. If there are gay people, then this doesn't quite fit into the context of bipartite matching, because if there are men attracted to men or women attracted to women, the graph is no longer bipartite. And there's nothing wrong with this necessarily, but it will make the problem computationally more complicated. Another example that you might want to consider is maybe a scheduling problem. You have sort of a bunch of events that need to be scheduled at different times. Each event has some blocks of time that would work for it, and you need to make sure that no two events get the same time block. Once again, sort of a bipartite matching problem. So, how are we going to solve this problem? The key idea is that there's a connection between this problem and network flows. Sort of what you want to solve in bipartite matching is you want to connect nodes on the left to nodes on the right without putting too many connections through a given node. This sounds sort of like a flow problem where you want to have flows running from left to right without too much flow running through any given node. So to make this work, you add source nodes and connect them to the left, and have the right nodes connect to a sink node and build up a network. So in particular, we start with our bipartite graph. You direct all of the edges left to right. We're going to add a source and a sink node. We're going to connect the source node to the vertices on the left and connect the vertices on the right to the sink. And we're going to define all the capacity edges of this graph to have capacity 1. This gives us a network associated to our bipartite graph. And it turns out that for every matching in our bipartite graph, there's a corresponding flow on the network. And so, to be formal about this, if G is the bipartite graph and G prime the corresponding network, there's actually a one-to-one correspondence between bipartite matchings on G and integer-valued flows on G prime. And just to prove this, well, if you have a matching, we can produce a flow by running flow through each edge of the matching. Then, to make everything balance out, each vertex of U, which we had flow running through it, we need to have flow coming to that vertex from S. And then that edge goes to some vertex in V, and that needs to extend through the edge to T. And that will give us a flow. Now, if we have a flow and want to go back to a matching, you just look at these middle edges between U and V and say which ones of them have flow, and those edges we use in the matching. Now, we can't have two edges coming out of the same vertex of U because there won't be enough flow going into that vertex. There's only one unit of flow going in at most, and so there can't be two units coming out. And we also can't have two edges sharing the same vertex on V for basically the same reason. And so there's a relationship between bipartite matching and integer-valued flows. However, you'll note that it was a lemma that we proved that you can always find an integer-valued maximum flow. And so our max flow algorithms sort of already work for solving this problem. So this gives us a very simple algorithm for solving bipartite matching. You construct the corresponding network, G prime. You compute a max flow for G prime in such a way that gives you an integer max flow. You then find the corresponding matching and return it. That solves the problem. Now, we could just say that we're done here, but there's something very interesting going on. So max flow min cut related the maximum flow to the minimum cut, which is sort of nice as a theoretical tool. But here, these bipartite graphs, the maximum matching relates to a max flow, and let's see what these cuts relate to. So if we have the network corresponding to a matching and look at a cut in this network, well, this cut contains the source, and it contains some set S of vertices on the left, and some set Y of vertices on the right. And we'd like to make this cut as small as possible. Now, if we fix X, the vertices on the right, well, when do they contribute to the cut? Well, vertices in Y, they have edges to T, which produce a one edge to the cut. But if you had an edge from X to a vertex not in Y, then that would also give you one edge that breaks the cut. And because of this, it actually can be shown that you can basically afford to just let your elements in V be your elements in Y be exactly the elements on the right-hand side that are connected to by some element of X. Now, if we do that, what edges break the cut? Well, you've got edges from S to elements of U that aren't in X. Now, by the way we constructed these, vertices in X only connect to vertices in Y that are also in the cut. But vertices in Y, they connect to T, and those also give you edges out of the cut. So the total size of the cut is the size of U minus X plus the size of Y. However, you'll note that all edges in G connect to either a vertex in Y or a vertex in U minus X. So one way to find a bound on your matching is by finding a set of vertices such that every edge in your graph connects to one of those vertices. And working this out gives us what's called Koenig's theorem, which says if G is a bipartite graph and K is the size of the maximal matching, then there has to be a set S of only K vertices of the graph, such that each edge in G connects to one of these vertices of S. And you'll note that if you have such a S, that gives you a bound on the maximal matching, because each edge needs to use up one of those vertices, and no two edges can share a vertex. And so Koenig's theorem says that the maximum matching on the graph is the same as the minimum, what it's called vertex cover, set S of vertices that connect to all edges. So, for example, if we have the following graph, you'll note that these four vertices connect to every single edge in the graph. So that says immediately the maximum matching has size at most 4, and it turns out that in this case it's tight. Now, there's one more special case of Koenig's theorem that's worth mentioning, That's the case where G is a bipartite graph with n vertices on each side. One thing that you might want to do is produce what's called a perfect pairing on G. That is a matching that uses every single vertex on both sides. Now, it's a theorem that if you sort of specialize Konig's theorem to this case, you can show that there's always a perfect pairing unless there's some set of only m vertices on the left-hand side, such that the total number of vertices that they connect to is strictly less than m. So you can always pair up your n men with your n women unless there's some collection of m men that pair with a total of fewer than m possible women. And if that's the case, these m men cannot all simultaneously have distinct dates, and so it's clearly not possible to produce your perfect pairing. So in summary, we've got this interesting problem of maximum matching, and we can solve it by reducing it to a problem of finding maximum flows. Furthermore, max flow min cut gives us some interesting characterizations of the sizes of this maximum matching. So that's all I have to say about bipartite matchings. Come back next lecture and we'll talk about one more problem that you can solve using this max flow technology that we've developed.